Then later I take out the square root. So if suddenly there's a severe outline, either on the left side or the right side, either way, that's going to create a very large deviation. Since I'm squaring it, I don't care about its sign. That's going to affect that average quite a bit. Taking the square root doesn't reduce its effect that much. So we need kind of a little bit robust alternative. And one alternative to this is, well, instead of squaring the deviations and taking the average, then taking the square root, what if we don't deal with any of the square root stuff? So one measure is mean absolute deviation, also known as MAD. And I'm gonna give that, let's call it S tilde, 1 over n, sum I equals 1 to n, maybe n minus 1, I don't know, doesn't matter that much. We're gonna use the Excel function. Remember, this is not a stats class. I don't care if you know that's n or n minus 1. I don't even know why they care, but they do. So you basically find the absolute deviation. Only the size matters, not the sign. And Excel function for that is come on. Which is short for average deviation, right? Just gonna copy this so that I can have the formats. Okay. As you can see, it's not as big as standard deviation. And remember, the units are exactly the same. I'm going to kind of introduce one thing here. I'm going to put an insanely large number for one of those inputs. And let's see the effect on standard deviation versus MAD. So instead of 155, I'm going to put 100. Control Z. So we're at 227 and 159. Standard deviation increased by a factor of almost 1.7, but MAD increased by a factor of maybe 15%. Let me see. Not even that. About 10%. That's what I mean by standard deviation being a less robust measure. I mean, they're both suffering from the fact that I'm still taking just the average, so an outlier still influences them, but standard deviation is affected a lot more. You're probably thinking, yes, I'm taking the square, but I'm taking the square root later. So doesn't that cancel that out? No, because you're taking out the square root of a sum after you square them, okay? Taking the square root does not dampen as much as taking the square inflates that sum. Because I'm taking the square root of the sum. Here, everything is of equal footing. So I suggest that you almost never use standard deviation as a measure of risk. You're going to use other measures of risk anyway, but if you just want to show somebody who doesn't know much about stats, what's the sigma here? Well, 1.7, okay? The sigma refers to population standard deviation. There's an old, and I make this into a joke. I don't know if you guys seen this when you took stats. There is something called empirical rule. You guys remember what that is? It basically says roughly 68% of the data should be within one standard deviation of the mean, about 95% two, almost all within three. The trouble with empirical rule is that A, it's not a rule, and there is nothing empirical about it, okay? That applies only if your data is pretty close to having a normal distribution. That's a property of normal distribution. That's why that's 95% and 2 are related. But, if things are in a normal distribution, man and standard deviation should be pretty close to each other. But for distributions that have much larger, much fatter tails, standard deviation is a lot less robust. You may, if I have time next week, I'm going to show you how to do it. You may ask yourself, if I'm really worried about robustness, how about I do a median absolute deviation from the median? It's almost a mad, okay, mad squared. You can. There is no given Excel function for that, but I'm going to actually show you guys how to write your own Excel function using VBA. We'll do some VBA, so we might as well get started next week on that. For now, kind of put it into your promise bank. I'm going to show you how to write an Excel function. Because we're going to do that when we're doing Black-Scholes pricing. There is no built-in Excel function for Black-Scholes, and I don't want to do things in a spreadsheet template because I want to be able to call that function anytime I want and get the value and get the Greeks of that. The Greeks are kind of measures of how certain inputs affect the price. Do you guys know why they're called Greeks? Just a trivia. Because all of them are named with Greek letters. You have a delta. It is the change in the value of an option when the underlying price changes by $1. And then there's gamma, which is the change in the delta when the underlying price changes by $1. You got the rho, that's for the interest rate. You got the theta, that's for passage of time. And you got vega, that's for volatility, so on and so forth. That's why they're called Greeks. I mean, the people who came up with the option pricing, they're from MIT, so I guess they wanted to show off the Harvard people. All right. And there is actually another much robust measure of dispersion. But until now, I'm just talking about things that are well known. This is called the interquartile range. First of all, when we say Q1, we say a value such that 25% of data points are at or below Q1. It's the first quartile or 25th percentile. You probably realize that Q2 is actually equal to median. Q3 is 75% of the data points are at or below that one. The IQR is Q3 minus Q1, right? And there is no function for IQR, but QI in Excel is quartile data I. Now, if I equals 0, that's actually gives you the minimum value. So if you want the minimum data point, that's I equals 1, Q1, or 25th percentile.